Hi, we want to look at curve sketching, and this time around we are concentrating on the inverse of a quadratic function if it exists. So here's the thing: if we have a quadratic function y equals to x squared, I think it's even more proper to say y equals to ax squared. Okay, provided a is positive. If we have that, we have this black curve here. Okay, but if we invert it, you get the green curve. Okay, and inverting just means that instead of looking at y equals to ax squared, you're looking at x equals to ay squared. Okay, and this is what you have. Of course, in this case now a is also positive, so let's say a is positive, and this is what you have. All right, that's the green curve here. So the green curve here is what you have if you sketch this. The problem is this cannot be an inverse function because this does not exist as an inverse. If you draw a straight line through this curve, it crosses the curve at 2 points, which means one input gives you two outputs. Okay, which defeats the definition of a function. So the best way to ensure that the inverse of a quadratic function exists is to restrict the domain of the function. You have to ensure that your function is one-to-one. So for instance, if you look at this curve y equals to x squared, and you can break it right from the middle here, what happens is you then close this one up, okay? And then you have only this portion. If you have only that portion, the inverse will be this portion. All right, I've got the graph here. Let me show you. So here it is. Here you've got y equals to x squared, the same one. The only thing is we've restricted the value on the x-axis. You will see that there is nothing used on the negative x-axis. So we've restricted it to x greater than or equal to 0. And that's why we have this graph here. Okay. Now, if you invert it, because finding the inverse means you are inverting it in the line y equals to x, which is the line that goes through the middle this way. Okay, ignore my wobbly line. That's y equals to x. Yeah, so if you invert it, you then get the blue line. And in this case, what you have is y equals to the root of x. Okay, I'll tell you how that equation was found. We originally had y equals to x squared. Now, because you are mirroring it in this line, and the line says y equals to x, replace x where y is. So you have x equals to y squared. Now, if you take the square root of both sides, what you will have will be y equals to the plus root of x, or y equals to the minus root of x. Now the problem is, since, well, it's not a problem, the consequence of choosing only x to be greater than 0 is that this is the only part we will now use. Okay, we will not need this down part for that domain. Okay, so this is what we're using, and that's why you only have this part of y being positive. Okay. So for some reason, people don't usually choose this other part. But I'd expect that if you chose the other part, which is that, and you reflect it, this is what you get as a reflection. The same process has been done, which is to reflect it in the line y equals to x. Okay, but more importantly, these functions are now one-to-one. So this one is one-to-one, because I don't think I demonstrated that yet. If you draw a straight line through this graph, you will see that it's only going to cut it at 1 point, which means you can get a single output. And this same one, of course, is now one-to-one. One input gives one output. So for the inverse of a quadratic function to exist, you have to limit its domain. Of course, you could have decided to make the domain just maybe from x greater than or equal to 2. So in that case, you cut it from this end and then erase this out, which totally will work, because when you invert it, you will also have from here upwards, and then this place is also erased. So it totally works. For the inverse to exist, make sure that your function is one-to-one. Okay, the next thing we want to do is to sketch the inverse function of this. Now, for us to even find the inverse function at all, we must limit the domain here to ensure that this function is one-to-one. If it's not one-to-one, we will not be able to find the inverse. And the reason for that is pretty simple. Quadratic curves usually are cups in that form, but if you find the inverse, they're usually like this. Well, in this case, this is not a function, because if you draw a vertical line, you will find out that it crosses the curve at 2 points, okay, which defeats the notion of a function. And this is why we need to limit the domain of a function. If we do that, say we are able to limit a function, the domain of a function, so that you just have maybe the right part of the curve going that way, when you find the inverse of that function, you would probably have something that goes this way also, and you will find that such a function will be one-to-one, because of course it passes the vertical line test. And this is why we have to limit the domain of the function. I hope I have not confused you further, but that you understand it. Even if there is some little confusion, please just keep watching. You will understand what I'm trying to say. Now, to write this in the form which I said earlier, what I need to do is to consider these two terms, and then what I do then is to pick the coefficient of x here, which is 2, take half of it, and then square it. And in essence, you will see that this gives me 1 squared, which then is equal to 1. And you will see that I already have that 1 here. And what that means is that this is already a square. It does not require us doing anything further. Now, if it's already a square, we then need to write it in that form so that it actually looks like it. And to do that, you pick one of the squares for x, and then you pick one of the squares for 1, then all squared. And you will find that if you expanded this, you will get this. If that's not, well, if you need more explanation on that, again, there's a video that I've made that clearly explains that and gives loads of examples which you could learn from. If you need to go watch it, that would be a good prerequisite for this video. If I have not linked it already sometime in this video, then I will link it right now. Now, what we would do next will be to limit the domain of this function, and I would do that by picking x greater than or equal to -1. Okay, so I've come to that conclusion because the minimum of this graph is at -1 and 0. How do I know? Because this is plus 0 here. So what you usually do is to pick the negative of this and the constant that is after it, which is 0. So I know the minimum is at -1 and 0. So which means we have a curve that maybe goes this way on a particular graph. Okay, and if this is -1, which means I'm choosing to pick the right hand side this way, and I am clearing out this part, which ensures that if you are to find the inverse, it will go this way, and you won't have the other part that will make it a non-function. I hope this is not confusing. So I've chosen that, the minimum is at that, and I've chosen the domain rightly. Now the next thing I'll do will be to find the inverse function so that I can actually sketch it. So I need to find the inverse function so that I can sketch it. Now how do I do that? Well, I have y now to be equal to x plus 1 all squared. This is another reason why this form is very important, because now it makes it very easy to make x the subject of the formula. Actually, I would like to switch first of all, so I will switch y to x and then this one to y. I have done that because if you have your curve and you want to find the inverse, it just means that you want to reflect it in the line y equals to x. So that's what I've done. I've simply switched y to x and switched x to y. And now I can make y the subject of the formula. Now if you do that, you will find that your y will equal to root of x minus 1. Again, you will notice that if I had taken the square root of both sides from here, I should be having plus or minus x, root of x, pardon, to be equal to y plus 1. But as you can see, I have only chosen the positive part. I did not choose this negative at all. The reason for that is the restriction I have put on the domain. I have ensured that for the domain, the minus x here will no longer be relevant. Okay, that's why I've chosen just the plus side. Now, what it then means is that if I had chosen x to be less than, say, minus 1, then I would have chosen only the negative side here, and I would have chosen y to be equal to minus root x minus 1 to sort out whatever problems I have. Okay. And to do that, first thing we want to look at is to look at the parent function of this, because that's the inverse. I should probably rewrite this as f inverse of x. Is to sketch y equals to root of x. And that is not difficult at all. This is just a graph that goes that way. That's y equals to root of x. Okay, now there is a minus 1 here, which tells me that I should go down 1 unit. So if I go down 1 unit, I then have my curve to look like this. So this is y equals to root of x minus 1. The only thing left for me to do is then to identify this point, which is easy because I went 1 unit down. That will be minus 1, and then identify this, which will be 1. How do I know that that will be 1? I know that at this point also y is 0, so I make y 0 in this equation, and then I have root of x minus 1. I take minus 1 over, and then I have root of x to be 1. And then if I square both sides, I'm going to have x to be 1 squared, which is also 1. Okay, and that concludes the sketching of the inverse function. If you have any question, please remember to drop it in the comments below. There's just one little thing I want to talk about. If the inverse function had been, let me put this in another color. If the inverse function had been y equals to root of x minus 1, the treatment will be different. This tells us that there is a horizontal movement, a positive horizontal movement, positive 1 unit horizontal movement. So what I would have done, instead of the graph, instead of this one here, because this is y equals to root of x, I would then have moved it 1 unit horizontally. It would not have gone below beneath the x-axis at all, and this one would have been y equals to root of x minus 1. So that explains the difference between this translation under the root and this one, okay, and this one that is outside of it. This is a vertical movement, while this is a horizontal movement. Well, I hope this helps, and then we'll move on to the next example. Okay, let's look at this other example. If you pay close attention, you see that there is a domain here, which you have to be careful with. Okay, now this function here, the first thing they've told us to do is to find its range. And I would always advise that if you can sketch the graph first, before you try to find the range of the domain so that you can actually see what you are choosing. Now to sketch this graph, we begin with the parent function. Remember that f of x equals to root of x is going to be the parent function of this. So we have that. That's literally what that gives you. Now, because you have plus 5 inside, it now tells you that you have to move your graph towards the left 5 units. So we move it towards the left 5 units. Let's do that. So now we have something that looks like that. Okay. Right. And then the minus here says that we should flip it over. So we'll flip it over so that we have something that looks like that. And because of that, I'm going to clean this one. Okay, now there is a plus 2. So we add 2. Remember that this one here, okay, will be at minus 5. X is minus 5, y is 0. So now if we lift it up maybe to y equals to 2, there, we are going to lift it up straight. So it means that the x will still be at minus 5, but the y will now be at 2. Okay, so let's lift it up right there. Okay, done. Now we are looking for 2 points that we need to consider. This part here, we know at that part there y is 0. So we're going to make y 0 in this formula there. Y is the same thing as f of x, so 0 equals to 2 minus root of x plus 5. If we take 2 to the other side, we cancel out the negatives, you get 2 equals to root of x plus 5. Square both sides, it gives you 4 equals to x plus 5. It gives you x to be minus 1. So we know that this is minus 1, comma 0. And then here we make we make x 0 because that's y axis. And then you will see that what you will have will be 2 minus root of 5. Okay, I don't want to change that to decimals because then the exact value will be lost. And we'll be dealing with decimals, which I don't want to do. So I'm leaving it that way. The only part left to maybe think about is the restriction of the domain. Now that we've sketched the graph, we have to remember that the domain has been restricted. So here we are good because it begins at minus 5, but it should end at 0. So there's been an extension there, which means that there's a part that we need to clean out. Okay, so let me see if I can redraw it so that I would cancel out the other parts. So if I redraw it, I will have this, that, and then it ends there. So let's see if I can cancel this out. Okay. Oh well, the original one is a bit more wobbly. Let me see. Okay, that's better, hopefully. All right, so that's what we have, and that is the sketch. It's now easy to state the range. Remember that the range is the y value. So if you look at it, the highest value for the y is at 2, as y equals to 2. And the lowest value is at 2 minus root of 5. Okay, so the range, if I'm going to write it down, would then be the lowest value first, which is 2 minus root of 5, is strictly less than f of x, and that is less than or equal to the highest value, which is 2. So that should be the range. Remember I put strictly less, but that's because of this one here. Okay, when we were doing the domain, remember that this one was strictly less than 0. So now that we are doing the range and it's the same point, you have to be very careful there. Okay, and make your f of x to be strictly less than that. Okay, so that is what we have for Roman figure 1. That is done. Now Roman figure 3 is also done because we have sketched the graph, so we are good with those two. Now Roman figure 2 says we should find the inverse function, so let's do that. To find the inverse function, remember that we are supposed to reflect in the line y equals to x, which means that all the y's become the x and all the x become the y. So let's flip that over. So instead of f of x here, I'm going to write x equals 2 minus, instead of x under the root, I'm going to write y plus 5. Because obviously x equals to y, y equals to x. And what I want to do now is to make y the subject of the formula. So x minus 2 will be equal to minus root of y plus 5. If I square both sides, I have x minus 2 all squared equals to y plus 5. So I will see that my y will be x minus 2 all squared minus 5. So we can write that as our f inverse of x equals to x minus 2 all squared minus 5. Now to state the domain and range, remember we said that if you are reflecting in the line y equals to x, all the x's become the y. Now, here are the x's, here are the y's. If they will be interchanging, it means that the domain will now become the range, because y comes to where x is and x comes to where y is. So the domain before is now the range, and the range before is now the domain. So that makes our job easier, isn't it? So for the domain, what was the range? Let's put it there. 2 minus root of 5 x is less than x, and that's less than or equal to 2. Remember that I changed from f of x to x. Okay, so that's the new domain. Now for the range of f inverse, what was the domain before? Minus 5 is less than or equal to. Now you write f of x, which is less than 0. And the job is done. Hopefully, I did everything, really well, and you enjoyed this video. Now, if you need more examples on this, just comment below and let me know so I could help you with it. Okay, see you next time. Don't forget to like this video and don't forget to subscribe so that any new thing comes out, you would enjoy, you will easily get it. Okay, see you next time. Bye-bye.